Jnanam paramam dhyeyam. Knowledge is supreme.
Summarizing whatever we did, take stock of what we did for the particle in a box, slowly getting on to bound states. Many of these things you know, but I am just trying to recap and get you onto the clarity of what we know, okay. So bound states, as I said, if the energy of the particle is less than potential at plus infinity and minus infinity, then we will have these one-dimensional bound state. So particle in a box definitely satisfies that condition, right? Everybody agrees? So it is a bound state solution. So all the solutions which we find, the wave functions and the corresponding energy, they are all bound state solution. Can you get scattering states in the particle in a box? Yes or no? No. Particle in a box solutions are all bound state solutions. Okay? And a couple of things which you would have mechanically done in the last semester or last year is taking the two wave functions, they are called orthonormal wave functions if they satisfy this property. I'm confining myself to one-dimensional potentials and they satisfy this property. This delta Nm is the Kronecker delta. I assume everybody knows. If n is equal to m, it is 1. If n is not equal to m, it is going to be 0. And this is what we call it as the normalized function. When n and m are equal, it is normalization condition. And when n and m are not same, they have to be orthogonal. So this whole thing is called as an orthonormal condition, or these wave functions, the stationary state solutions of the particle in a box are supposed to be called as orthonormal wave functions if they satisfy this property. Is that okay? So that's the definition, and we always try to do this. We always try to find a set of stationary states which are normalized and also orthogonal to each other for convenience, because we write any arbitrary state as a linear superposition of these stationary states. Okay, so this I did go through in the last lecture. I thought for continuity, let me put in here. So bound system, it's confined to a finite region, and the familiar harmonic oscillator where the force should be proportional to the displacement with a negative sign here. Proportionality constant is a spring constant from which you can derive what is the potential energy, and putting in a boundary condition like x equal to 0, we want the potential to be 0, will give you a potential energy to be half kx square. Okay. So we would like to solve the time independent Schrodinger equation for this one-dimensional harmonic oscillator, and this one also satisfies the boundary condition that V at plus or minus infinity is infinity, and your energy is always going to be less than V at plus infinity and V at minus infinity. So this one is also a bound state solution. Okay. So since it's time independent potential energy, we can write the time dependent wave function with the appropriate energy of the stationary state multiplying it. So how do we go about it? We try to substitute in the time independent Schrodinger equation, and we also impose wave function to vanish as we go to the boundary which is plus or minus infinity. Is that right? So we could formally assume a solution which is, which is having some kind of an fn of x with some function of x multiplying an e a to the power of x squared. This is just a formal solution. You can call it as a trial solution. You can try and find out whether it fits into the equation. So as of now, let's assume that this trial wave solution will allow us to fix what is the A value, what is the small a value, what is the capital A value, what is the Fn of x, where this n denotes the stationary states of energy En. Okay, is that clear? Okay, so for n equal to 0, which is the lowest state, we take f naught of x to be 1 and we want to verify whether this is an allowed solution when we plug into this equation. Okay, so for convenience, just to make the equation look neater, we will redefine the energy to be proportional to alpha with these proportionality constant. Similarly, instead of x, we will put in a factor, pre-multiplying it and call that to be rho. You can also write x by a naught, where a naught is this factor. A naught is h cross by m omega under square root. So once you substitute into the time independent Schrodinger equation, please verify this in terms of the alpha variable and rho variable. It looks in this simple form. Please verify this from the previous slide. Here it is E and also X. Convert them into the rho variable and instead of E, use the alpha variable and rewrite that equation. Please do this, okay. So the equation becomes simplified to be of this form. We are doing it for the lowest n equal to 0, which we will call it as a ground state. So now we will put in the boundary condition. What is the boundary condition? Psi vanishes as x tends to plus or minus infinity, which is also equal to rho tending to plus or minus infinity, because the pre-multiplying a naught factor is just a constant factor. It is not x dependent. And you can also for convenience make another change of variable and make it look like your familiar equation. So as rho tends to infinity, I can neglect alpha and rewrite in terms of another variable t, which I am calling it to be rho square. Don't confuse this t with some time or anything, some other variable, and rewrite it in terms of this variable t and take this is valid only for rho tending to infinity and therefore t should tend to infinity. Okay. So this is not, this equation is the simplified equation when rho is very large. You all agree? Because only when rho is very large I can ignore this alpha term. Is that right? So what is the solution to this equation? You have done this many times, right? E to the t by 2, this is k squared is 1 by 4, right? So e to the kx plus e to the minus kx, is that right? So the solution will be a e to the power of minus t by 2 plus b e to the power of plus t by 2. And out of this, as t tends to infinity, which is allowed? Only the first term, so you have to put b equal to 0, right? So you get the allowed solution as a e power minus rho squared by 2. So this I have done with some kind of a trial solution, putting into the equation, and what is the trend when rho is very large or x is very large? I find the trend has to be this way, and this is normalizable. From there you can find what is the normalization constant. Conversely, this you would have done in your first year course. You are given this wave function, right? Here we found the solution by looking at the time independent Schrodinger equation in the large rho limit. But instead you can assume this is the solution and substitute, right? This you have done as far as I know. What do? You substitute, take the derivative, again you take the double derivative because that is what is required in your time independent Schrodinger equation, right? After you have done this, you have the time independent Schrodinger equation with this incorporated solution given to you to check whether it satisfies. But this is what you get. Then what do? Still not clear to me that this is a solution. How do I check that? You have to compare both sides for every power of x, because this is valid for any x. So you should be able to compare left hand side and right hand side for every value of x. E to the ax squared anyway cancels throughout. You can remove it and compare powers of x on both sides. Okay. So, from there what can we fix? We can fix the small a. We can also fix the energy. Is that right? The term which is E, there are two x squared terms. The two x squared terms can be set to 0, the sum of these two terms. Similarly, this is a constant independent of x. This should be equated to E. So, do that. Equate the constant term to E and equate the x squared term, this equal to this. So, from there you can solve for what is a, small a, and what is capital E, and it turns out to be half h cross omega, and the a can be fixed to be this constant. So, once you have this, you can write your most general solution, rewriting your x in terms of rho as the solution. So, I have given you two ways of finding the solution, and we have verified that this is a valid solution. Okay. So, rho is up to those factors proportional to x, and normalization condition will fix for you what is the normalization factor. What is this integral going to give you? Square root of pi divided by 2 square root of 2a, right? Everybody knows the gamma function. Can I assume? Okay. So, that gamma function, if you use, then you can fix the normalization condition, what mod of a squared is. Is that okay? Okay. So, that is the normalization condition, and this gives us a complete solution for the ground state, psi 0 of x. You can rewrite it in terms of rho for convenience, but you can replace it back and rewrite it in terms of the physical x coordinate, and there is a normalization factor. So, E naught is the ground state energy, and unlike your classical physics, where if I ask you what is the ground state energy for a harmonic oscillator, you would have said it is 0, right? Classical energy is 0, but quantum mechanics solving time independent Schrodinger equation, the lowest energy turns out to be non-zero, which is half h cross omega. So, just to get you back to the time independent Schrodinger equation, we saw that for large rho, you can try to simplify the equation and write the most general solution as this, and taking t tending to infinity will force us to look at only psi of x, which is a e to the power of minus rho squared by 2, as we have seen. There's few transparencies behind. Okay. So, what is my aim? My aim is to try and find, so that is the trend for large rho, but for finite rho, for any rho, I should be able to write my solution to the time independent Schrodinger equation, which we have not done. So far we have looked at the solution for large rho, and there was a trial solution also of the same form, and we verified, we found the energy, and the energy was half h cross omega. Ideally you should do the solution to the Schrodinger equation for any rho, which we didn't do. So let us assume that the wave function which we have, okay, is some function of rho multiplying e to the minus rho squared by 2. Later on we will put what is rho in terms of x. That is just a matter of redefinition. For convenience we will work with the variable rho. Okay. You plug this into the time independent Schrodinger equation, which is what we will do. Substitute this in the time independent Schrodinger equation. Alpha is proportional to energy. Looking at this, can we say what is the solution? It's not obvious. if you go and look at the mathematical special functions, you can determine what the solution is. But we would like to do this from first principles, how to find the solution. To do that, what do? You had an exponential factor here. You would like to put this to be some kind of a polynomial function. In principle, it could be an infinite series. Call it as some Lorentz series if you want. This is the most general h of rho I can think of taking in a polynomial form. So, once I have this h of rho in this polynomial form, I plug this back into the simplified time independent Schrodinger equation where this factor got cancelled out throughout, right? Then what do you get? You get kind of a series which are dependent on the coefficients. ANs are the coefficients. You get a series like this. For every power of rho of r, you can group the terms accordingly. Please do the step. Go from this step to this step by substituting h of rho. Please substitute h of rho, and then for a particular rho power rho of r, group all the terms which I have written it in square bracket. And then the r is running from 0 to infinity. Why have I done this? What is the reason for doing this? This should be the solution for arbitrary rho. So, the bracket, square bracket coefficient should be 0 for every power of rho. Just like earlier we did comparing x independent and x squared dependent term for a simplest ae power ax squared. Now we are going to do it for substituting in this, which is a most general solution valid for any rho. So, what are the things which you will have? So, you can try to rewrite. If you see from this, there is always the square bracket involves coefficients which are in steps of only 2. Okay. So, this relation setting it to 0 will relate a r plus 2 in terms of AR. Okay. Everybody is with me? Is that right? You don't get AR plus 2 in terms of AR plus 1. What does that tell us? I can split my h of rho into two pieces, one involving odd powers, one involving even powers, and the coefficients of even powers are related by this. Similarly, the odd powers are related by this. When r is even, the coefficients are related by this, with r being even, and when r is odd, the coefficients are related by this, where r is odd. Okay. So, this is the data we get by taking h of rho as a polynomial series, plugging into the Schrodinger equation. We find that the coefficients are not independent. The coefficient of the respective powers, even powers or odd powers, they are related to the lower coefficients with this factor which depends on alpha. Alpha is proportional to energy, right? That's the definition we had. Okay. So, what was the alpha proportional to? Alpha is proportional to the energy. Okay. Okay. So, this I have already said that you can, from this condition, you can write h of rho with series with even powers of rho with the coefficients of the higher powers related to the lower coefficients, and similarly another series with odd powers of rho. So don't confuse this R with any radial coordinate or position. This R is a subscript R in the coefficients which are there in the power series which we wrote for h of rho, okay. A subscript R. Let's take R, this subscript R to be very large. If I take R to be very large, then this R is very large. You can ignore these constants and you will end up saying that when the coefficients of large subscript R, they will be related to the lower coefficients by 2 over R. My aim is to find the solution. That is why I am trying to do from first principle, rather than looking at the Schrodinger equation and going and looking at the mathematician's literature to find the solution. I am not doing that. I am giving you a way in which you can try to actually find the solution by taking a general power series h of rho times e to the minus rho squared by 2. And e to the minus rho squared by 2 happened for large rho in the Schrodinger equation. We saw that. Is that okay? So then what next? You have to, this solution should also be a valid solution for large rho. When you take rho to be large, the an coefficients, the dominant contribution will come from an's where n is very large, right? Is that right? So for large rho, you can approximate h of rho, it's not exactly equal, by taking this AR. This you can do only for large rho because the dominant contribution will come from those coefficients. So you can approximate h of rho for large rho to look like c to the power of rho squared. Is this allowed? Is this allowed? This, when rho tends to infinity, it blows up. So it is not allowed, right? You all agree? So what is the way out of this? How? So this is not allowed. So I am getting stuck if I take an infinite series polynomial solution for h of rho. Let's work with finite series polynomial solution. That is the only way I can avoid my wave function not to blow up, okay. So this is not normalizable. The way out is to take h of rho to be a finite series. But how finite you should take? Whatever finite you want to take, that means at some point you have to put this coefficient for some specific r to be 0. That is the meaning of saying it is a finite series. Once you put that to be 0, then by this relation, recursion relation, all the higher powers will be 0. So let's put an plus 2 to be 0. Once I put an plus 2 to be 0, then the only way this will be 0 is that alpha will be equal to 2n plus 1. Once I get alpha equal to 2n plus 1, can somebody tell me what will be the energy? So what is alpha? E by 2e by h cross omega, right? And alpha is n plus 1, alpha is 2n plus 1. So then E, let me put the E to be as subscript n now, 2en by h cross omega is 2n plus 1. So which implies En is h cross omega n plus half. So the solution is to take, if you want normalizable solutions, infinite series for h of rho will not work, finite series will work, and I can truncate wherever I want, okay, by putting an appropriate n. Here I started with an plus 2 equal to 0. So what is the solution? The solution is h of rho will be summation over n even from 0 to some specific value. So let me write it as r 0 to n So you take it only in steps of even numbers, an rho n. So that your psi of rho is some normalization constant, let me call it as psi n, hn of rho times e to the power of minus rho squared by 2, and the corresponding En is h cross omega n plus half. I have still not written these Ans, but I have given you a recursion relation here from which you can determine what is An in terms of An minus 2 and so on, okay. So this is one possible solution. Another possible solution is n could be odd, okay, and you can write another solution where, so this is n is even. You can also have a similar solution for n equal to odd, but the Hn series will involve only odd powers, okay. So these are the possible solutions whose power series, finite power series can be determined also from the time independent Schrodinger equation, and you can go and compare with the special functions later, okay. This is one route a person who doesn't know what is the solution to the complicated differential equation can actually do it this way. So the solution for the nth state where n is even implies that the corresponding energy is this, and you can set the odd powers, the lowest odd power to be 0. Once you put the lowest odd power to be 0, by this recursion relation, odd powers don't show up at all, right? And or you could do for the n odd where you can put the lowest even power to be 0, which is A0. So those are the two solutions which I have written. N is odd and n is even. Okay.